This graph summarizes some of the general shapes that we might see for budget sets and the implications it has for the possibility that there might be one or more than one optimal solution for a consumer. What we'll see is that if the budget constraint is convex, then there'll be a single optimal solution. If it is non-convex, there might be multiple optimal solutions. We begin with a blue budget line that starts out shallow and becomes steeper and steeper. Any indifference curve that starts out steep and becomes shallower and shallower can then be at most tangent to this budget constraint at a single point. As a result, there's only a single optimal solution for a consumer facing such a budget constraint. The reason for this is that the budget set that's formed by this budget constraint is a convex set, in the sense that you can choose any two bundles that lie within that set, and the line connecting those two bundles will also be fully contained within that set. One example of such a budget constraint was illustrated in graph 6.5, where the budget constraint was formed by two line segments, beginning with a shallow segment followed by a steep segment, creating an outward kink and a convex budget set. Next, we illustrate a magenta budget line that has the usual linear shape, and for the usual reasons, there's now a single optimal solution, much as there was in panel A. This again results from the fact that the budget set created by this budget constraint is a convex set. Any two bundles have the feature that if they lie within the set, the line connecting them also is fully contained within the set. Next, we illustrate a green budget constraint, but now we start it steep and make it shallower and shallower as we go along. This creates the possibility for two optimal solutions, point A and point B, for the gray indifference curve that's graphed. The reason for this is that we now have a non-convex budget or choice set. You can choose bundle A and bundle B, for instance, and the line connecting A and B lies fully outside the budget set, even though points A and B are part of the budget set. This is what creates the possibility for two optimal solutions. Finally, we draw another blue budget constraint, but this time start with a steep line segment followed by a shallow line segment, much as we did in graph 6.6. And again, we get the possibility of two optimal solutions, one at bundle A and one at bundle B, for the gray indifference curve that's illustrated. This is happening for exactly the same reasons as it did in panel C of the graph. The kink was not necessary to obtain the possibility of two optimal solutions. Rather, what creates that possibility is the non-convexity of the budget set. We began in panel A with a budget constraint that bent outward from the origin, and this gave rise to a very strict convexity of the budget or choice set. In panel B, we straightened out that budget constraint, but we're still left with a convex budget set. Then, in panel C, we took that budget constraint and bent it inward toward the origin, and this gave rise to a non-convexity in the budget set. Finally, we showed in panel D that we can get that same non-convexity with an inward kink of the budget constraint. It's important to note that the two optimal solutions illustrated in panel C and D are only possibilities. We could have chosen to draw an indifference curve in such a way that there was indeed still only one optimal solution. The non-convexity in budget constraints therefore merely creates the possibility that there may be more than one optimal solution. It's also important to note that throughout we assumed that tastes themselves were still convex, giving rise to the usual shapes of indifference curves. We'll see what happens when that assumption is violated in graph 6.8.